What if the emptiest regions of the universe, the vast hollows between galaxies where nothing seems to exist, are actually humming with more energy than all the stars combined? Tonight, we'll step quietly into the hidden truth about empty space, a truth so strange that it suggests the vacuum itself might be the most powerful force in all of existence. From quantum fields that never rest to virtual particles flickering in and out of being, from the mysterious dark energy stretching our cosmos, to the zero-point vibrations that refuse to disappear even at absolute zero, we'll explore what really fills the void. And if this gentle journey into the heart of nothingness brings you even a moment of wonder, a quiet tap on subscribe helps keep these midnight stories alive beneath the stars. Your support means more to me than you might imagine. Now, let's begin to uncover what actually powers empty space. Part 1. For centuries, empty space was the simplest concept in all of physics. Take a glass jar, pump out every molecule of air, remove every speck of dust, cool it to absolute zero, and what remains is nothing at all. Newton imagined space as an infinite, invisible stage where matter performs its cosmic dance, a perfectly empty container that stays the same whether planets move through it or not. This absolute space was humanity's baseline for understanding reality, the zero against which everything else could be measured. Einstein shattered that comfortable picture when he showed that space and time are woven together, bending and flexing like a fabric under the weight of matter and energy. Suddenly, empty space had geometry, curvature, and dynamics. But even Einstein's revolutionary spacetime seemed fundamentally passive, responding to matter but containing nothing of its own. The real problem emerged when physicists tried to understand forces. How could the sun pull on Earth across 93 million miles of apparently empty void? Newton himself admitted this troubled him deeply. He wrote to Richard Bentley in 1692 that the idea of gravity acting through empty space was so absurd that no person competent in philosophical thinking could ever accept it. Yet the mathematics worked perfectly, predicting planetary orbits with stunning accuracy. Scientists learned to calculate with invisible forces while privately wondering what actually carried them across the emptiness between objects. Maxwell's electromagnetic theory deepened the mystery. His equations described electric and magnetic fields rippling through space at the speed of light. But fields of what exactly? Many physicists imagined a substance called the ether, an invisible medium that filled all of space and carried electromagnetic waves like water carries ripples. The Michelson-Morley experiment in 1887 destroyed that hope, finding no trace of any cosmic medium. Light waves somehow travelled through pure nothingness, a fact that seemed to violate every intuition about how waves should behave. Einstein resolved this paradox by eliminating the need for an ether, but his solution left space even more mysterious. In his relativity, electromagnetic fields were fundamental features of space-time itself, requiring no underlying substance. This was intellectually satisfying but conceptually strange. Empty space now possessed electric and magnetic properties without being made of anything that could possess such properties. The quantum revolution of the 1920s would soon reveal that this classical picture of emptiness was not just incomplete but profoundly wrong. Werner Heisenberg discovered that nature imposes fundamental limits on how precisely we can know certain pairs of properties simultaneously. You cannot measure both the position and momentum of a particle with perfect accuracy, no matter how sophisticated your instruments become. This uncertainty principle seemed like a limitation of measurement technology until physicists realized its deeper implication. If uncertainty is built into the fabric of reality itself, then perfect emptiness becomes impossible. Consider what perfect vacuum would mean in quantum terms. Every field at every point in space would have exactly zero energy, zero fluctuation, zero activity. But Heisenberg's principle forbids such precision. The energy of any field must fluctuate, and those fluctuations can never completely disappear. Even when you remove all matter, all radiation, all heat, and cool everything to absolute zero, the quantum fields themselves continue to vibrate with what physicists call zero-point energy. This discovery emerged from the careful study of simple harmonic oscillators, the quantum version of masses attached to springs. Classical physics predicts that such a system should have zero energy when it comes to rest at the bottom of its potential well. Quantum mechanics reveals that this classical ground state violates the uncertainty principle. Instead, the oscillator must retain a minimum energy of half a quantum unit, forever jiggling even at absolute zero temperature. Since quantum field theory describes every point in space as a harmonic oscillator for each type of field, the vacuum becomes a seething sea of irreducible quantum activity. The electromagnetic field alone contributes zero-point energy at every frequency, from radio waves to gamma rays, at every point throughout infinite space. When Max Planck first calculated this zero-point contribution in 1912, he found something remarkable. The vacuum is not empty but contains an energy density that makes the core of the Sun look calm by comparison. Modern estimates suggest that each cubic centimetre of empty space contains approximately 10 to the power of -9 joules of energy, which might sound small until you consider that this energy density is perfectly uniform throughout the observable universe. The total zero-point energy in a volume the size of a light bulb exceeds the energy released by burning a tank of gasoline, but this energy remains forever locked in quantum fluctuations that average to zero when measured with classical instruments. This strange new picture of vacuum emerged gradually from careful experiments that detected the fingerprints of zero-point energy in atomic behavior, spontaneous photon emission, and tiny shifts in electron energy levels that classical physics could not explain. In 1927, Werner Heisenberg discovered that the universe operates under a fundamental rule that makes perfect knowledge impossible. His uncertainty principle states that you cannot simultaneously know both the exact position and exact momentum of any particle, no matter how precise your measuring instruments become. This is not a limitation of technology, but a basic feature of reality itself. The mathematics is deceptively simple. The uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to Planck's constant divided by 4p. But hidden within this elegant equation lies a second, even more profound relationship that would revolutionize our understanding of empty space. Heisenberg realized that the same uncertainty applies to energy and time. If you try to measure the energy of any system with perfect precision, the time it takes to make that measurement becomes completely uncertain. Conversely, if you observe a system for only a very brief moment, its energy becomes fundamentally uncertain by an amount inversely proportional to that time interval. The mathematical expression is identical in form. Delta E times delta T must be greater than or equal to h bar over 2, where h bar is Planck's reduced constant. This energy-time uncertainty principle opened a doorway to understanding the impossible. For the briefest moments allowed by quantum mechanics, the universe can borrow energy from nowhere, create something from nothing, and then quickly return that energy before any violation of conservation laws can be detected. The shorter the time interval, the more energy can be borrowed. These quantum loans operate on timescales so brief that they exist below the threshold of direct measurement, yet their effects permeate every corner of the physical world. The implications struck at the heart of what physicists meant by empty space. True vacuum would require every field to have exactly zero energy at every point, but the uncertainty principle forbids such precision. Instead, quantum fields must fluctuate constantly, even when cooled to absolute zero and isolated from all external influences. These fluctuations represent the minimum possible energy that any quantum system can possess, dubbed zero-point energy because it persists even at zero temperature, where classical physics predicts all motion should cease. Max Planck first encountered this concept while studying blackbody radiation in 1912 and 1913. He was trying to understand why heated objects glow with specific colours at specific temperatures, a problem that had resisted classical solutions. When Planck applied the new quantum theory to electromagnetic fields inside a heated cavity, he found that each vibrational mode of the field carried energy in discrete packets or quanta. But even more surprising was his discovery that each mode retained a residual energy of half a quantum unit, even when no thermal energy was present. This zero-point energy appeared as an unavoidable consequence of treating light as both wave and particle, a prediction so strange that Planck himself initially doubted its physical reality. The experimental proof came through careful observations of atomic behavior that classical physics could not explain. When an electron in an excited atomic state drops to a lower energy level, it emits a photon in a process called spontaneous emission. Classical electromagnetic theory suggested that an excited electron should remain in its high-energy state indefinitely unless disturbed by external radiation. Yet experiments clearly showed that electrons spontaneously emit photons and decay to lower states even in perfect isolation from external fields. The quantum explanation revealed that even empty space contains enough electromagnetic fluctuation to trigger these transitions. The zero-point energy of the electromagnetic field provides the gentle push that causes excited atoms to release their excess energy. This phenomenon occurs throughout the universe, from the cores of distant stars to laboratory experiments on Earth, confirming that the vacuum itself participates actively in atomic processes. Laboratory measurements of spontaneous emission rates agreed precisely with calculations that included zero-point energy, but disagreed dramatically with classical predictions that ignored vacuum fluctuations. Further evidence emerged from studies of the Lamb shift, tiny deviations in hydrogen spectral lines discovered by Willis Lamb and Robert Rutherford in 1947. Their precise measurements revealed that electron energy levels in hydrogen atoms differed slightly from the values predicted by the Dirac equation, which had successfully explained all other aspects of electron behavior. The discrepancy arose from the interaction between electrons and zero-point fluctuations of the electromagnetic field. Even in perfect isolation, electrons experience a constant buffeting from virtual photons popping in and out of existence on timescales too short to observe directly. These quantum fluctuations shift electron energies by measurable amounts, providing concrete evidence that empty space seethes with invisible activity. The Lamb shift experiments earned a Nobel Prize and established zero-point energy as an experimentally verified feature of nature rather than a mathematical curiosity. Today, spontaneous emission and the Lamb shift stand as cornerstones of quantum electrodynamics, the most precisely tested theory in all of science, with predictions verified to better than 1 part in a trillion. When physicists finally calculated the energy density of empty space, they discovered something that challenged everything they thought they knew about the universe. Modern quantum field theory predicts that every cubic meter of vacuum contains approximately 10 to the power of -9 joules of zero-point energy. This might seem like a tiny amount until you grasp what it means on cosmic scales. The vacuum energy density throughout the observable universe may actually exceed the energy contained in all visible matter, from the smallest asteroids to the largest galaxy clusters. To understand this staggering realization, consider that the mass energy of all the stars, planets, gas clouds, and dark matter in the observable universe amounts to roughly 10 to the power of 54 joules. The zero-point energy in the same volume, calculated using the observed cosmological constant, totals approximately 10 to the power of 69 joules. Empty space contains 100,000 trillion times more energy than everything we can see. This energy remains hidden from direct detection because it represents the baseline state of quantum fields, the zero against which all other energies are measured. We cannot extract this energy or use it to power our devices, because doing so would require lowering the vacuum to a state with less than zero-point energy, which the uncertainty principle forbids. Yet this invisible energy ocean influences the cosmos in profound ways, potentially driving the accelerated expansion of the universe itself through its gravitational effects. The theoretical foundation for vacuum energy emerges from treating every point in space as a quantum harmonic oscillator for each type of field that exists. In classical physics, a harmonic oscillator is simply a mass attached to a spring oscillating back and forth with a characteristic frequency. When the mass comes to rest at the spring's equilibrium position, the system has zero energy. Quantum mechanics transforms this picture completely. The uncertainty principle prevents any oscillator from coming to perfect rest, because that would require knowing both its position and momentum with infinite precision. Instead, every quantum oscillator must retain a minimum energy equal to half its characteristic frequency multiplied by Planck's constant. This zero-point energy can never be removed or reduced, representing an irreducible quantum jiggling that persists even at absolute zero temperature. Quantum field theory extends this concept to every point throughout space. The electromagnetic field, for example, can be decomposed into an infinite collection of harmonic oscillators, one for each possible frequency and direction of oscillation at each location. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays all contribute their zero-point energies to the vacuum. The electron field adds its own zero-point contribution, as does the muon field, the quark fields, the neutrino fields, and every other field described by the standard model of particle physics. Each oscillator vibrates independently with its characteristic frequency, creating a complex symphony of quantum fluctuations that fills every cubic centimetre of space. These fluctuations occur on timescales far too brief for direct observation, yet their collective effects shape the structure of reality itself. Virtual particle pairs constantly appear and disappear throughout the vacuum, borrowing energy from the zero-point field for fleeting moments before annihilating and returning that energy to the quantum reservoir. Electron-positron pairs flicker into existence near atomic nuclei, briefly altering the electric fields that bind electrons to atoms. Virtual photons mediate electromagnetic forces between charged particles, carrying momentum and energy across empty space. Quantum chromodynamics describes how virtual gluons bind quarks together inside protons and neutrons, while virtual W and Z bosons enable radioactive decay processes that power the stars. The mathematics underlying these phenomena has been verified to extraordinary precision through decades of careful experiments. Quantum electrodynamics, the theory describing electromagnetic interactions including vacuum fluctuations, makes predictions that match experimental measurements to better than 1 part in a trillion. The anomalous magnetic moment of the electron, the Lamb shift in hydrogen spectra, and the rate of spontaneous photon emission all depend critically on zero-point energy contributions. These measurements confirm that the vacuum behaves exactly as quantum field theory predicts, a seething ocean of activity rather than passive emptiness. Recent experiments have begun to manipulate vacuum fluctuations directly, demonstrating their tangible reality. Researchers at MIT have used intense laser fields to control quantum fluctuations in free space, generating random bit sequences for quantum computing applications. Teams at Chalmers University of Technology in Sweden have created the dynamic Casimir effect, using rapidly changing electromagnetic boundaries to convert virtual photons into real ones that can be detected and measured. These experiments represent humanity's first tentative steps toward engineering the quantum vacuum itself. The realization that empty space contains vast reserves of energy has profound implications for our understanding of cosmic evolution, the nature of matter, and the ultimate fate of the universe. Every galaxy swims through an ocean of vacuum energy that dwarfs the combined mass of all its stars. Every atom exists within a quantum foam of virtual particles that influence its properties and behavior. The vacuum is not the absence of everything, but the presence of infinite possibility. A quantum stage where the drama of existence unfolds against a background of ceaseless, invisible activity. Virtual particles represent one of the most misunderstood concepts in modern physics, existing at the boundary between mathematical formalism and physical reality. They are not particles in the conventional sense that you could catch in a detector or observe directly, but rather represent the quantum mechanical fluctuations of underlying fields that permeate all of space. These fluctuations emerge naturally from the uncertainty principle, which allows energy to be borrowed from the vacuum for brief periods, creating temporary disturbances in quantum fields that behave somewhat like particles, but with properties that would be impossible for real particles to possess. The concept of virtual particles arose in the 1940s, when physicists developed quantum field theory to describe how particles interact with each other. Richard Feynman revolutionized the field by inventing a diagrammatic method for visualizing and calculating these interactions. In Feynman diagrams, real particles that you can detect in experiments appear as external lines entering and leaving the diagram, while virtual particles appear as internal lines connecting the interaction vertices. These internal lines represent quantum processes that occur during the interaction, but cannot be observed directly because they happen faster than any measurement could detect. Virtual particles violate the fundamental relationship that governs all real particles. Einstein's energy-momentum equation E squared equals pc squared plus m naught c squared squared, where E is energy, p is momentum, m naught is rest mass, and c is the speed of light. Real particles must satisfy this equation exactly, but virtual particles can have energies and momenta that differ dramatically from what this relationship would allow. A virtual photon, for example, might carry energy and momentum that would be impossible for a real photon, which must be massless and travel at the speed of light. This violation is permitted because virtual particles exist for time so short that the uncertainty principle prevents any measurement from detecting the violation. The mathematics of virtual particles emerges from perturbation theory, a computational technique for calculating how quantum systems behave when interactions are weak enough to treat as small corrections to simpler, exactly solvable cases. When two electrons repel each other electromagnetically, the complete quantum mechanical calculation involves summing an infinite series of increasingly complex processes. The simplest process involves the exchange of a single virtual photon between the electrons. More complex processes include the virtual photon temporarily converting into a virtual electron-positron pair before reconverting back to a photon, or multiple virtual photons being exchanged simultaneously. Each term in this infinite series corresponds to a different Feynman diagram with a different arrangement of virtual particles. The remarkable discovery of quantum electrodynamics is that this series converges rapidly, meaning that the first few terms provide extremely accurate predictions for experimental results. The exchange of a single virtual photon accounts for most of the electromagnetic force between charged particles, while higher-order corrections involving more virtual particles produce tiny but measurable effects that have been verified to extraordinary precision. Virtual particles appear not just in electromagnetic interactions, but in all fundamental forces. The strong nuclear force that binds quarks together inside protons and neutrons operates through the exchange of virtual gluons. The weak nuclear force responsible for radioactive decay involves virtual W and Z bosons. Even gravity, according to quantum theories still under development, would involve virtual gravitons. Each type of virtual particle carries the characteristic properties of its corresponding force, allowing physicists to understand how forces operate at the deepest level. The interpretation of virtual particles has sparked decades of philosophical and scientific debate. Some physicists argue that virtual particles are merely mathematical tools, useful for calculations but not corresponding to anything that actually exists in nature. They point out that virtual particles cannot be directly observed and that alternative mathematical formulations of quantum field theory, such as lattice field theory, achieve the same results without invoking virtual particles at all. From this perspective, virtual particles are convenient fictions that help physicists organize their calculations but should not be taken as literal descriptions of physical processes. Other physicists argue that virtual particles represent genuine physical phenomena, even if they cannot be observed directly. They emphasize that virtual particles have measurable consequences through their effects on real particles, and that many experimental results can be most naturally understood in terms of virtual particle processes. The Casimir effect, for example, is often explained as arising from virtual photons that exist between conducting plates, and spontaneous emission of radiation from excited atoms is frequently described as stimulated by virtual photons in the vacuum. Recent experiments have added new dimensions to this debate by demonstrating that virtual particles can produce effects that seem almost real. Quantum energy teleportation protocols show that the energy associated with virtual particles can be extracted and transferred between distant locations, suggesting that these mathematical constructs may have more physical substance than previously thought. These experiments operate entirely within the framework of standard quantum mechanics, while revealing that the boundary between virtual and real phenomena may be more subtle than traditional interpretations suggested. The uncertainty principle grants the universe a remarkable license to violate energy conservation, but only if the violation is paid back quickly enough to escape detection. This quantum loophole operates through the energy-time uncertainty relation, which states that the uncertainty in energy multiplied by the uncertainty in time must exceed Planck's constant divided by 4pi. In practical terms, this means that for extremely brief moments, the universe can borrow arbitrary amounts of energy from the vacuum, create particles that should not exist, and then destroy them before any measurement could reveal the violation. The shorter the time interval, the more energy can be borrowed without consequence. This principle enables the constant creation and annihilation of virtual particle pairs throughout empty space, a process that transforms the vacuum from passive emptiness into an active participant in every physical interaction. Virtual particle pairs appear spontaneously throughout the quantum vacuum, with electron-positron pairs being among the most common. An electron and its antimatter counterpart, the positron, can materialize from pure energy fluctuations for brief moments before annihilating each other and disappearing back into the vacuum. The energy required to create this pair must be borrowed from quantum fluctuations, but the uncertainty principle allows this debt, as long as the particles recombine quickly enough. The more massive the particle pair, the more energy must be borrowed, which means heavier particles can exist for shorter times before the quantum debt comes due. Electron-positron pairs, being relatively light, can persist for longer periods than virtual proton-antiproton pairs, which require much more energy to create. Virtual photons represent another common type of quantum fluctuation, appearing as disturbances in the electromagnetic field that mediate forces between charged particles. Unlike virtual electron-positron pairs, virtual photons are massless and can be created with any energy, but they still must respect the time-energy uncertainty relation. High-energy virtual photons carry large momentum and can travel only briefly before disappearing, while low-energy virtual photons can persist longer and travel farther. This creates a spectrum of virtual photon exchanges that collectively produce the electromagnetic force we observe between charged objects. The process of virtual particle creation and annihilation happens continuously throughout space at every point and at every moment. Quantum field theory calculates that in any cubic centimetre of vacuum, virtual electron-positron pairs appear and vanish at a rate of approximately 10 to the power of 42 events per second. Virtual photons flicker in and out of existence even more rapidly, creating a seething foam of activity that remains completely invisible to direct observation, but profoundly influences the behaviour of real particles. These virtual fluctuations affect atomic structure by slightly altering the energy levels of electrons bound to nuclei. The Lamb shift, discovered in hydrogen atoms, arises because virtual photons briefly knock electrons away from their average positions, changing the electrostatic energy that determines atomic spectra. Virtual electron-positron pairs also contribute by creating a cloud of virtual charge around real electrons that screens their electric fields, an effect known as vacuum polarization. The timing constraints imposed by the uncertainty principle create strict rules for virtual particle behavior. A virtual electron-positron pair created with the minimum energy possible, approximately 1.02 million electron volts, can exist for at most 10 to the power of minus 21 seconds before violating energy conservation. Higher energy pairs must disappear even faster, while lower energy virtual photons can persist longer. This creates a hierarchy of virtual processes, with low-energy, long-lived fluctuations producing subtle, long-range effects and high-energy, short-lived fluctuations causing dramatic but brief disturbances in quantum fields. The annihilation of virtual particle pairs must occur through the reverse of the creation process, with the antimatter particle encountering its matter counterpart and converting their combined mass back into the energy fluctuation that originally created them. This annihilation returns the borrowed energy to the vacuum, balancing the quantum books and ensuring that no net energy is created or destroyed. The precision of this process is extraordinary, with virtual particles appearing and disappearing in perfect synchronization to maintain energy conservation on average, even while individual events may temporarily violate it. Recent experiments have begun to probe these virtual processes more directly by using intense electromagnetic fields to influence the rate at which virtual pairs are created and destroyed. When subjected to extremely strong electric fields, virtual electron-positron pairs can be prevented from recombining, converting virtual particles into real ones that can be detected experimentally. This process, known as the Schwinger effect, requires field strengths far beyond current laboratory capabilities, but it may occur naturally near black holes and neutron stars where gravitational fields approach the theoretical limits of space-time itself. The question of whether virtual particles truly exist or merely represent mathematical conveniences has divided physicists for decades, creating one of the most enduring controversies in quantum field theory. On one side stand those who argue that virtual particles are nothing more than computational artifacts, useful for organizing calculations but bearing no relationship to physical reality. They point out that virtual particles cannot be directly observed, violate fundamental conservation laws, and can be eliminated entirely from theoretical frameworks without changing any experimental predictions. Alternative formulations of quantum field theory, such as lattice field theory used in supercomputer simulations, achieve identical results without ever invoking virtual particles, suggesting that these entities are merely human constructs rather than features of nature itself. On the opposing side are physicists who maintain that virtual particles represent genuine physical phenomena, albeit ones that exist in a realm between classical reality and pure abstraction. They emphasize that virtual particles have measurable consequences through their effects on real particles, and that many experimental observations can be most naturally understood through virtual particle processes. John Wheeler, the visionary physicist who coined the term black hole, proposed one of the most influential pictures of virtual particle reality through his concept of quantum foam. Wheeler suggested that at the smallest scales of space and time, near the Planck length of 10 to the power of minus 35 meters and the Planck time of 10 to the power of minus 44 seconds, space-time itself becomes a seething froth of quantum activity. Virtual particles constantly pop into existence and vanish again, creating fluctuations in the fabric of reality so violent that the very concepts of space and time lose their classical meaning. In Wheeler's vision, virtual particles are not separate entities moving through space, but rather represent the quantum jittering of space-time itself, making them as fundamental to reality as the dimensions in which we live. The debate intensifies when considering how forces operate between particles through virtual particle exchange. When two electrons repel each other electromagnetically, quantum field theory describes this interaction as the exchange of virtual photons that carry momentum and energy between the charges. The virtual photons cannot be detected directly, yet they produce precisely the force that classical physics attributes to electric fields. Critics argue that this description is purely metaphorical, a storytelling device that helps physicists visualize mathematical equations but should not be taken literally. Proponents counter that the virtual photon exchange provides the only known mechanism by which forces can operate without requiring action at a distance, making virtual particles essential for understanding how the universe actually works, rather than merely how it can be calculated. Recent experiments have added new evidence to both sides of this philosophical divide, while revealing that the boundary between virtual and real may be more fluid than previously thought. In 2008, Masahiro Hotta at Tohoku University proposed quantum energy teleportation, a protocol that seemed to extract energy from virtual particles and transfer it instantaneously across space. The proposal was largely ignored until 2019, when researchers at Stony Brook University and 2021 teams in Germany successfully demonstrated the effect in laboratory settings. These experiments showed that information about quantum fluctuations can be used to extract energy from the vacuum at one location by performing specific measurements at another location. The extracted energy comes from virtual particles, yet it can be measured and used to perform real work, blurring the distinction between virtual and actual phenomena. The quantum energy teleportation experiments operate by exploiting quantum entanglement between different regions of the vacuum. When researchers make carefully designed measurements on quantum fields at one location, they can instantaneously affect the energy available for extraction at distant locations connected through quantum correlations. The process respects all known conservation laws and never allows faster-than-light communication, but it demonstrates that virtual particles can have tangible effects that extend beyond mere calculation tools. These results have sparked renewed interest in the ontological status of virtual particles, with some physicists arguing that anything capable of transferring real energy must possess some degree of physical reality. The controversy continues to evolve as new experimental techniques probe ever more subtle aspects of quantum field theory. Researchers using atomic force microscopes have measured forces between individual molecules that can only be understood through virtual particle exchanges, while teams studying superconducting circuits have observed signatures of virtual photon interactions in quantum devices. Each new experiment adds layers of complexity to the debate, revealing that virtual particles exhibit properties that seem almost but not quite real, existing in a liminal space between mathematical abstraction and physical substance that may reflect fundamental limitations in how humans understand the quantum world, rather than deficiencies in the virtual particle concept itself. In 1948, a young Dutch physicist named Hendrik Casimir, working at Philips Research Laboratories, made a prediction so counterintuitive that it challenged the very notion of empty space. Casimir had been studying the van der Waals force, the weak attraction between neutral atoms, when a conversation with Niels Bohr led him to consider what would happen if two perfectly conducting metal plates were placed very close together in a vacuum. Classical physics suggested that no force should exist between electrically neutral objects separated by empty space, but Casimir's quantum mechanical analysis revealed something extraordinary. The electromagnetic field between the plates would be restricted in ways that created a measurable attractive force, even in perfect vacuum. His calculation began with the recognition that electromagnetic fields can be described as collections of harmonic oscillators, each vibrating at a specific frequency and contributing zero-point energy to the vacuum. In empty space without boundaries, all possible frequencies and wavelengths of electromagnetic radiation can exist, creating an infinite sea of quantum fluctuations with uniform energy density. However, when conducting plates are introduced, they impose boundary conditions that dramatically alter this picture. The electric field must vanish at the surface of a perfect conductor, which means that electromagnetic waves can only exist between the plates if they fit exactly into the gap, like standing waves in a musical instrument. Only wavelengths that are integer multiples of twice the plate separation can survive between the conductors, while all other frequencies are excluded from the gap. Casimir realized that this restriction fundamentally changed the zero-point energy density between the plates compared to the unrestricted vacuum outside. Each allowed electromagnetic mode contributes half a quantum of energy to the vacuum, so reducing the number of modes reduces the total zero-point energy in the gap. The energy density outside the plates remains at its normal vacuum level, creating an energy difference that manifests as a physical force pushing the plates together. The calculation required summing over all allowed frequencies between the plates and subtracting this from the zero-point energy of unrestricted vacuum, a process that initially yielded mathematical infinities that had to be carefully handled using regularization techniques. The final result was elegant and precise, the attractive force per unit area between perfectly conducting plates separated by distance d equals pi squared times Planck's constant times the speed of light divided by 240 times d to the fourth power. This force varies inversely with the fourth power of the separation, making it extremely strong at small distances, but negligible at large separations. For plates separated by 1 micrometer, the predicted force amounts to approximately 1.3 micropascals, equivalent to the pressure exerted by a thin sheet of paper. While tiny by everyday standards, this force becomes enormous compared to other quantum effects and should be easily measurable with sensitive instruments. Casimir's prediction implied that the vacuum itself could exert mechanical forces on matter, a concept that seemed to violate fundamental assumptions about the nature of empty space. The scientific community initially met Casimir's work with considerable skepticism. Many physicists found it difficult to accept that virtual quantum fluctuations, which could not be observed directly, could produce real mechanical forces measurable in laboratory experiments. The idea that empty space between conducting plates contained less energy than empty space elsewhere seemed to contradict basic intuitions about vacuum being uniformly empty. Some researchers questioned whether the mathematical techniques used to handle infinite sums in the calculation were physically meaningful or merely mathematical artifacts. Others worried that the idealization of perfectly conducting plates might not correspond to any realizable experimental situation, making the prediction untestable in practice. The theoretical foundation itself faced challenges from physicists who preferred alternative interpretations of quantum field theory that did not rely on zero-point energy concepts. Despite these concerns, Casimir's prediction represented a crucial test of quantum field theory's ability to make concrete predictions about macroscopic phenomena. If the effect could be measured experimentally, it would provide direct evidence that quantum vacuum fluctuations have observable consequences beyond their role in atomic physics. The force would demonstrate that the electromagnetic vacuum is not passive emptiness, but an active medium that can influence the motion of material objects. Conversely, if careful experiments failed to detect the predicted force, it would cast doubt on fundamental aspects of quantum field theory and the physical reality of zero-point energy. The theoretical elegance of Casimir's derivation, combined with its clear experimental implications, gradually won over skeptics and established the Casimir effect as a legitimate prediction of quantum electrodynamics that demanded experimental verification. The stage was set for decades of increasingly sophisticated experiments designed to test whether the quantum vacuum could indeed reach across empty space and pull metal plates together with forces predicted by the strange mathematics of quantum field theory. 10 years after Casimir's theoretical prediction, Dutch physicist Marcus Sparnay at Philips Research Laboratories in Eindhoven undertook the first experimental attempt to detect the elusive force between conducting plates in vacuum. Working with the same institution where Casimir had made his original prediction, Sparnay faced technical challenges that seemed almost insurmountable with 1950s technology. The Casimir force operates only at extremely small separations, typically less than a micrometer, where it must be distinguished from much stronger electrostatic forces that arise from even tiny amounts of electrical charge on the metal surfaces. Sparnay's experimental design involved two flat metallic mirrors made from aluminum, chromium or steel, mounted in a vacuum chamber and brought to within a few hundred nanometers of each other, using precision mechanical controls. He measured the force between the plates using a sensitive spring balance whose extension could be determined by monitoring the electrical capacitance between the plates as their separation changed. The greatest challenge proved to be eliminating electrostatic interference, since any residual electric charge on the plates would create attractive or repulsive forces many thousands of times stronger than the predicted Casimir effect. To address this problem, Sparnay developed an ingenious technique of touching the plates together briefly before each measurement, allowing any accumulated charge to redistribute and neutralize. This procedure had to be repeated frequently because cosmic rays and other ionizing radiation constantly deposited small amounts of charge on the isolated metal surfaces. Even with careful charge, neutralization, residual electrostatic effects remained a persistent source of experimental uncertainty that threatened to overwhelm the tiny quantum mechanical force. The requirement for the perfect parallelism between the plates created another formidable obstacle. The Casimir force depends on the fourth power of the plate separation, meaning that even tiny deviations from perfect parallelism would create large variations in force across the surface of the plates. If one edge of the plates was separated by 200 nanometers, while the opposite edge was separated by 300 nanometers, the force difference between these regions would be a factor of 5, creating torques and non-uniform stresses that would completely mask the uniform attraction predicted by Casimir's theory. Sparnay spent months developing mechanical systems capable of maintaining parallelism to better than 10 nanometers across plates measuring several square centimeters in area, a precision that pushed the limits of available engineering techniques. Vibrations from laboratory equipment, thermal expansion of the mounting apparatus, and gravitational settling of the entire experimental setup all conspired to introduce unwanted variations in plate separation that had to be carefully controlled or compensated. The actual force measurements required extraordinary sensitivity because the predicted Casimir attraction amounted to only a few hundred piconewtons for the plate sizes and separations that Sparnay could achieve. This force is comparable to the weight of a few hundred molecules, far below the detection threshold of conventional mechanical instruments. Sparnay's spring balance system could barely resolve forces at this level, and external vibrations from passing traffic, building settling, and even seismic activity from distant earthquakes threatened to introduce noise that would completely obscure the signal he was trying to measure. Each measurement required hours of careful data collection under the most stable conditions he could arrange, with results that often scattered widely due to uncontrolled environmental factors. Despite these formidable technical challenges, Sparnay's measurements showed a consistent pattern of attractive forces between the plates that increased rapidly as the separation decreased, qualitatively matching the distance dependence predicted by Casimir's theory. However, the experimental uncertainties were so large that Sparnay could only conclude that his results did not contradict the theoretical prediction rather than providing definitive confirmation. The measured forces were consistently attractive rather than repulsive, eliminating some alternative explanations for the effect, and they showed approximately the correct dependence on plate separation and material properties. But the error bars on individual measurements often exceeded 50% of the predicted force, making it impossible to claim quantitative agreement with theory. Sparnay's cautious conclusion that his experiments did not contradict Casimir's prediction marked an important milestone in experimental physics, providing the first empirical evidence that quantum vacuum fluctuations might indeed produce observable mechanical effects. His work established the basic experimental techniques for studying the Casimir effect, while clearly demonstrating the formidable challenges involved in measuring forces at the intersection of quantum mechanics and macroscopic physics. The modest success of these pioneering measurements inspired decades of subsequent experiments using increasingly sophisticated technologies, each building on Sparnay's foundational work while pushing toward the precision needed to transform qualitative consistency into quantitative verification of one of quantum field theory's most counterintuitive predictions. Nearly 40 years after Sparnay's pioneering but inconclusive measurements, technological advances finally enabled physicists to achieve the precision necessary for definitive tests of the Casimir effect. In 1997, Stephen Lamoureux at the University of Washington revolutionized Casimir force measurements by developing a torsion pendulum system that could detect forces with unprecedented accuracy. Lamoureux's apparatus consisted of a gold-coated spherical lens suspended from a thin, tungsten wire, positioned above a flat gold-coated plate mounted on piezoelectric actuators for precise positioning. The sphere plate geometry offered crucial advantages over the parallel plate configuration used in earlier experiments because it eliminated the need for perfect parallelism while still producing measurable Casimir forces. When the spherical surface approached the flat plate, quantum vacuum fluctuations created an attractive force that caused the pendulum to twist by a measurable angle. Lamoureux monitored this deflection using a laser interferometer capable of detecting angular displacements smaller than a billionth of a radian, corresponding to forces as small as 10 piconewtons. His careful control of electrostatic effects, achieved through precise voltage applications and surface preparation techniques, reduced systematic errors to unprecedented levels. The results agreed with Casimir's theoretical predictions to within 5%, providing the first quantitative confirmation that quantum vacuum fluctuations could indeed produce measurable mechanical forces between macroscopic objects. Building on Lamoureux's breakthrough, Umar Mohideen and Anushree Roy at the University of California, Riverside pushed precision even further by adapting atomic force microscopy techniques to Casimir effect measurements. Their experiments used a 200 micrometer diameter polystyrene sphere attached to the cantilever of an atomic force microscope, with the sphere and a flat silicon surface both coated with thin layers of gold or aluminum. This configuration allowed them to measure forces at separations as small as 60 nanometers while maintaining exquisite control over the experimental geometry. The atomic force microscope's laser deflection system could detect cantilever movements corresponding to forces as small as 1 piconewton, and careful calibration procedures eliminated most sources of systematic error. Mohideen and Roy's measurements agreed with theoretical predictions to better than 1% accuracy at the closest separations, establishing the Casimir effect as one of the most precisely verified predictions of quantum field theory. Their work demonstrated that the attractive force between a gold-coated sphere and plate reaches approximately 100 piconewtons when separated by 100 nanometers, exactly matching the quantum mechanical calculations within experimental uncertainty. Subsequent experiments by research groups worldwide have refined these measurements even further, testing the Casimir effect with different materials, geometries, and environmental conditions. Teams led by Roberto Decker at Indiana University, Purdue. University Indianapolis achieved sub-% precision using improved sphere plate configurations, while Giuseppe Bermonte at the University of Naples developed techniques for measuring Casimir forces in liquid environments. These experiments have confirmed theoretical predictions across separation ranges from few nanometers to several micrometers, validating quantum field theory's description of vacuum fluctuations with extraordinary precision. The experiments have also tested subtle corrections to the basic Casimir effect, including finite conductivity effects in real metals, surface roughness corrections, and thermal contributions that become important at larger separations. Perhaps the most dramatic recent development has been the observation of the dynamic Casimir effect, predicted in the 1970s, but not successfully demonstrated until 2011. This phenomenon occurs when the boundary conditions of the electromagnetic field change rapidly, converting virtual photons into real ones that can be detected experimentally. Christopher Wilson and colleagues at Chalmers University of Technology in Sweden achieved this effect using a superconducting quantum interference device to rapidly change the effective length of a microwave resonator cavity. By modulating the cavity at frequencies near twice the resonant frequency, they created conditions where virtual photons could become real photons, observing the production of the microwave radiation from pure vacuum fluctuations. This experiment represented humanity's first success at directly converting the quantum energy of empty space into detectable radiation, confirming theoretical predictions about the dynamic response of the quantum vacuum to changing electromagnetic boundaries. The dynamic Casimir effect has since been observed in other systems, including metamaterials with time-varying properties and semiconductor structures with modulated optical properties. These experiments have opened new research directions, in quantum optics and may eventually lead to practical applications for converting vacuum energy into usable forms. Modern Casimir effect experiments continue to push the boundaries of precision measurement while exploring exotic geometries and materials that could reveal new physics beyond the standard model. Current research includes measurements between superconducting surfaces, tests of the Casimir effect in curved spacetimes, and investigations of repulsive Casimir forces that occur with certain combinations of materials and media. In 1917, Albert Einstein faced a profound problem that threatened to undermine his newly completed theory of general relativity. His field equations, which described how matter and energy curve spacetime, made a disturbing prediction about the universe as a whole. It could not remain static. According to Einstein's mathematics, any universe containing matter must either expand or contract under the influence of gravity, with no possibility of remaining perfectly still. This prediction contradicted the prevailing scientific wisdom of the time, which assumed that the cosmos was eternal, unchanging and infinite in extent. Astronomers had detected no evidence of cosmic expansion or contraction, and the very idea that the universe as a whole could evolve seemed philosophically unacceptable to most scientists, including Einstein himself. Faced with this apparent conflict between his theory and observation, Einstein made a fateful decision that would later become one of the most famous examples of scientific regret in history. To salvage the possibility of a static universe, Einstein modified his field equations by adding a new term called the cosmological constant, represented by the Greek letter lambda. This additional term acted as a repulsive force that operated over cosmic distances, counterbalancing the attractive pull of gravity to create a stable, static cosmos. The cosmological constant represented energy inherent to space itself, a uniform energy density that filled the vacuum throughout the universe, and produced negative pressure that opposed gravitational collapse. Einstein carefully calculated the exact value needed to balance gravity and create a static solution to his equations, deriving a universe that was finite in size but without boundaries, curved back on itself like the surface of a sphere but in higher dimensions. This ingenious mathematical fix allowed general relativity to accommodate the apparently static universe that astronomers observed, but it came at the cost of introducing an arbitrary parameter into the theory that had no independent physical justification. Einstein himself felt uncomfortable with this modification, describing the cosmological constant as theoretically unsatisfying because it destroyed the mathematical elegance and simplicity that had originally motivated his approach to relativity. The cosmological constant solution was also unstable, requiring precisely the right balance between matter density and vacuum energy to remain static, like a pencil balanced on its point. Any small perturbation would cause such a universe to either expand or contract catastrophically, making it difficult to understand how a static cosmos could have persisted for the vast ages that astronomical observations suggested. Despite these theoretical concerns, the cosmological constant seemed necessary to reconcile general relativity with the observational fact that stars and galaxies appeared to maintain fixed positions relative to each other over human timescales. This comfortable compromise between theory and observation lasted for more than a decade, until Edwin Hubble's revolutionary observations using the 100-inch telescope at Mount Wilson Observatory completely transformed our understanding of cosmic structure. Between 1924 and 1929, Hubble made two crucial discoveries that shattered the assumption of a static universe. First, he proved that spiral nebulae were actually distant galaxies far beyond the Milky Way, vastly expanding the known scale of the cosmos. Second, and even more dramatically, he discovered that these distant galaxies were moving away from us, with their recession velocities proportional to their distances in a relationship that became known as Hubble's law. The universe was not static but expanding, with space itself stretching and carrying galaxies apart like raisins in rising bread dough. Hubble's discovery meant that Einstein's original field equations had been correct in predicting cosmic evolution, while the cosmological constant modification had been unnecessary and misleading. Einstein quickly abandoned the cosmological constant, later reportedly calling its introduction his greatest blunder because it had prevented him from predicting the expansion of the universe that his unmodified theory would have naturally described. The realization that he could have anticipated one of the most important astronomical discoveries of the 20th century purely through theoretical reasoning became a source of lasting regret for Einstein, who had temporarily lost faith in the predictive power of his own equations. For decades following Hubble's discovery, the cosmological constant was largely forgotten by physicists, dismissed as an unfortunate detour in the development of modern cosmology. The expanding universe described by Einstein's original field equations seemed to provide a complete and elegant description of cosmic evolution, requiring no additional parameters or assumptions. The standard model of cosmology that emerged from this period assumed that the expansion was gradually slowing down under the influence of gravity, eventually leading either to eternal expansion at decreasing rates or to eventual collapse in a big crunch, depending on the total amount of matter in the universe. In 1988, American astrophysicist Saul Perlmutter launched an ambitious project that would fundamentally transform our understanding of the universe's fate. The Supernova Cosmology Project aimed to measure the deceleration of cosmic expansion by observing type I supernovae, stellar explosions so bright they could be detected across billions of light-years of space. These supernovae served as ideal cosmic yardsticks because they always reached approximately the same peak brightness, allowing astronomers to determine their distances by comparing their apparent brightness to their known intrinsic luminosity. By measuring both the distances and redshifts of these distant stellar explosions, Perlmutter's team hoped to trace the expansion history of the universe and determine whether it would expand forever or eventually collapse under its own gravity. The project required developing new techniques for systematically discovering supernovae in distant galaxies, using wide-field CCD cameras and automated image analysis software to scan thousands of galaxies simultaneously for the telltale brightening that signals a stellar explosion. In 1994, a competing team called the High-Z Supernova Search Team began pursuing the same goal under the leadership of Brian Schmidt from the Australian National University, with Adam Rees from the University of California, Berkeley, playing a crucial role in the data analysis. Both teams spent years refining their observational techniques, calibrating their measurements, and accumulating data on dozens of distant supernovae spanning cosmic distances from hundreds of millions to several billion light-years. The expectation was clear: gravity should be slowing the expansion of the universe, so distant supernovae should appear brighter than predicted by simple linear expansion, because the universe was expanding faster in the past when their light was emitted. Instead, both teams discovered exactly the opposite result that would revolutionize cosmology and restore Einstein's cosmological constant to a central role in our understanding of the cosmos. In 1998, after years of careful observations and analysis, both teams announced their shocking findings. Distant supernovae appeared dimmer than expected, indicating they were farther away than predictions based on decelerating expansion would suggest. Rather than slowing down, the expansion of the universe was speeding up, accelerating at an ever-increasing rate under the influence of some mysterious repulsive force that had only recently begun to dominate cosmic evolution. The implications were staggering because no known form of matter or energy could produce such an effect. Ordinary matter and radiation create gravitational attraction that should slow expansion, while even exotic forms of matter like hot gas or relativistic particles could at best create pressure that might slow the deceleration, but never cause acceleration. The observations demanded the existence of something completely unprecedented, a form of energy with negative pressure so strong that its gravitational effect was repulsive rather than attractive. Cosmologist Michael Turner quickly coined the term dark energesis to describe this mysterious component, emphasizing both its invisibility to direct detection and its profound ignorance about its fundamental nature. The supernova results suggested that dark energy comprised approximately 70% of the total energy density of the universe, making it the dominant component of cosmic evolution despite being completely unknown to physics. Both research teams conducted exhaustive checks of their data and methods, searching for systematic errors that might explain away the surprising results. They considered possibilities including gravitational lensing by intervening matter, evolution in the properties of supernovae over cosmic time, and absorption of light by cosmic dust, but none of these effects could account for the observed dimming without creating additional contradictions with other astronomical observations. Independent confirmation came from studies of the cosmic microwave background radiation and large-scale galaxy clustering patterns, which showed that the geometry and matter content of the universe were consistent with the supernova measurements when dark energy was included in cosmological models. The accelerating universe discovery earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics for their revolutionary transformation of cosmology through careful observational work. Their findings not only revealed the existence of dark energy, but also restored Einstein's cosmological constant as a viable explanation for cosmic acceleration. If dark energy maintains constant density as the universe expands, it would behave exactly like Einstein's cosmological constant, representing an intrinsic energy of empty space that produces repulsive gravity. However, alternative explanations including quintessence fields with evolving energy density and modifications to general relativity on cosmic scales remain active areas of theoretical and observational research as scientists work to understand the ultimate fate of an accelerating universe dominated by dark energy. The discovery of cosmic acceleration revealed that approximately 68% of the universe consists of dark energy, a mysterious component that exerts negative pressure strong enough to overcome gravity and drive the accelerating expansion of space itself. This dark energy represents the largest constituent of cosmic energy density, dwarfing the contributions from ordinary matter at 5% and dark matter at 27%, yet its fundamental nature remains one of the deepest puzzles in modern physics. The defining characteristic of dark energy is its negative pressure, which creates gravitational repulsion rather than attraction, according to Einstein's general relativity. While ordinary matter and radiation have positive pressure that enhances their gravitational attraction, dark energy's negative pressure is so extreme that its repulsive gravitational effect overwhelms its attractive mass energy contribution by a factor of 3 to 1. This unusual equation of state, where pressure equals -1 times the energy density, drives cosmic acceleration by causing space itself to expand at an ever-increasing rate, stretching the fabric of space-time and carrying distant galaxies away from us with accelerating velocities. The leading theoretical candidate for dark energy is Einstein's cosmological constant, now reinterpreted as the quantum mechanical energy of empty space itself. Quantum field theory predicts that the vacuum contains zero-point energy fluctuations of all possible quantum fields, from photons to electrons to more exotic particles described by the standard model of particle physics. If this vacuum energy has the properties of Einstein's cosmological constant, it would maintain constant density as the universe expands because new space brings new vacuum with the same energy density, creating exactly the negative pressure needed to drive acceleration. The cosmological constant interpretation links dark energy directly to the quantum mechanical properties of empty space, suggesting that the vacuum itself is the dominant component shaping cosmic evolution. However, this identification faces a catastrophic theoretical problem known as the vacuum energy crisis, or cosmological constant problem, where quantum field theory calculations predict a vacuum energy density that exceeds observations by more than 120 orders of magnitude, the largest discrepancy between theory and experiment in the history of physics. Alternative explanations for dark energy include quintessence, a hypothetical scalar field that fills space with dynamical energy density that can evolve over cosmic time. Named after the fifth element of ancient philosophy, quintessence fields would behave like slowly rolling balls in potential energy landscapes, with their kinetic and potential energies combining to create the negative pressure needed for acceleration. Unlike the cosmological constant, quintessence energy density can change as the universe evolves, potentially providing solutions to both the cosmic acceleration and the cosmological constant problem by allowing the dark energy to approach zero in the far future. Quintessence models predict subtle signatures in cosmic microwave background radiation patterns and supernova distance measurements that could distinguish them from cosmological constant behavior, making them actively testable through precision astronomical observations using facilities like the Euclid Space Telescope and the Vera Rubin Observatory. More radical alternatives propose modifications to general relativity itself on cosmic scales, suggesting that our understanding of gravity breaks down when applied to the universe as a whole. These modified gravity theories attempt to explain cosmic acceleration without invoking dark energy by proposing that gravitational interactions become repulsive at very large distances or that additional spatial dimensions affect cosmic evolution in ways that mimic dark energy effects. Some models propose that gravity becomes weaker on cosmic scales due to leakage into extra dimensions predicted by string theory, while others suggest that quantum corrections to general relativity become important when applied to the entire observable universe. Dark energy might also arise from interactions between ordinary matter and previously unknown fields or particles that become important only at cosmic scales and densities. Phantom dark energy represents another exotic possibility where the energy density actually increases as the universe expands, eventually becoming so dominant that it tears apart all gravitational structures in a catastrophic Big Rip scenario. Current observational evidence suggests that dark energy behaves very much like Einstein's cosmological constant, maintaining nearly constant density as the universe expands and producing acceleration consistent with a simple negative pressure equation of state. Precision measurements from the Planck satellite, large galaxy surveys, and Type A Tau supernova observations all point toward a cosmological constant-like behavior, but the error bars remain large enough to accommodate slowly evolving quintessence fields or more exotic alternatives. Future astronomical missions, including the Nancy Grace Roman Space Telescope and ground-based surveys like the Dark Energy Spectroscopic Instrument, are designed to measure the evolution of cosmic acceleration with unprecedented precision, potentially revealing whether dark energy truly represents the energy of empty space or requires more exotic explanations that could revolutionize our understanding of fundamental physics and the ultimate fate of the cosmos. When physicists first attempted to calculate the energy density of empty space using quantum field theory, they encountered what would become known as the most embarrassing prediction in the history of physics. The calculation begins with the fundamental principle that every quantum field must exhibit 0-point fluctuations at every point in space, with each field mode contributing a minimum energy of 1/2 times Planck's constant times its characteristic frequency. To find the total vacuum energy density, quantum field theory requires summing these contributions over all possible field modes, including electromagnetic fields at every frequency from radio waves through visible light to gamma rays and beyond, plus additional contributions from electron fields, muon fields, quark fields, neutrino fields, and all other fundamental particles described by the Standard Model. Each type of field oscillates independently at every point in space, creating an enormous collection of quantum harmonic oscillators that must be included in the energy tally. The electromagnetic field alone contains an infinite number of modes because electromagnetic waves can have any frequency and can oscillate in any direction at every location throughout space. Classical physics would predict zero energy for these modes in the absence of external sources, but quantum mechanics demands that each mode retains its irreducible 0-point energy even at absolute zero temperature. When physicists attempt to sum these 0-point contributions, they encounter mathematical infinities that require careful treatment using regularization and renormalization techniques developed specifically for quantum field theory calculations. The most straightforward approach involves imposing a high-frequency cutoff, assuming that quantum field theory becomes invalid above some maximum energy scale where new physics must take over. The natural choice for this cutoff is the Planck energy scale, approximately 10 to the 19th power GeV, where quantum gravitational effects are expected to become important and the usual rules of quantum field theory break down. Using this Planck scale cutoff in the calculation yields a vacuum energy density of approximately 10 to the 113th power joules per cubic meter, a number so astronomical that it defies comprehension. To put this in perspective, this predicted energy density exceeds the mass energy of an atomic nucleus compressed into a volume the size of a proton by more than 40 orders of magnitude. If this calculation were correct, the vacuum energy in a volume the size of a coffee cup would exceed the total mass energy of all visible matter in the observable universe. Such enormous energy density would create gravitational effects so extreme that space-time itself would curl up into microscopic dimensions, preventing the formation of atoms, stars, galaxies, or any structures larger than the Planck length. The universe predicted by this naive quantum field theory calculation would consist entirely of quantum black holes forming and evaporating on Planck timescales, with no possibility for the stable, large-scale cosmos that we actually observe. In stark contrast to this theoretical catastrophe, observational astronomy provides a precise measurement of the actual vacuum energy density through studies of cosmic acceleration and the cosmological constant. Supernova observations, cosmic microwave background measurements, and large-scale structure surveys all consistently indicate that the vacuum energy density is approximately 10 to the negative 9th power joules per cubic meter, smaller than the quantum field theory prediction by a factor of 10 to the 122nd power. This represents the largest discrepancy between theoretical prediction and experimental observation in the entire history of science, exceeding even the most notorious failures of classical physics by more than 100 orders of magnitude. The vacuum energy density that astronomers observe is so small that it only recently became the dominant component of cosmic energy density, taking over from matter, dominance when the universe was already 3/4 of its current age. This observed dark energy drives cosmic acceleration at the gentle rate of about 7% per billion years, barely detectable except through the most sensitive astronomical observations of distant supernova and cosmic structure formation. The discrepancy between the quantum field theory prediction and astronomical observations represents far more than a simple calculational error or missing correction term. The magnitude of the disagreement suggests a fundamental gap in our understanding of how quantum mechanics and gravity interact, pointing toward new physics that might emerge from string theory, extra dimensions, supersymmetry, or completely unknown principles that govern the relationship between quantum fields and space-time curvature. Some physicists have proposed that the vacuum energy density is exactly zero due to some unknown symmetry or cancellation mechanism, making the observed cosmological constant arise from entirely different physics, while others suggest that our understanding of quantum field theory itself requires revision when applied to cosmological scales, where gravitational effects become important. The 123 order of magnitude discrepancy between quantum field theory's prediction for vacuum energy and astronomical observations represents the most spectacular failure in the history of theoretical physics, earning the infamous nickname of the vacuum catastrophe or cosmological constant problem. To appreciate the sheer magnitude of this discrepancy, consider that most scientific measurements agree with theoretical predictions to within a few percent, while even the most notorious failures of classical physics, such as the ultraviolet catastrophe and blackbody radiation, involved errors of only a few orders of magnitude before quantum mechanics provided the correct description. The vacuum energy problem dwarfs all previous theoretical failures by an almost incomprehensible margin, suggesting either that quantum field theory fundamentally breaks down when applied to cosmological scales, or that some completely unknown physics cancels the vacuum energy with extraordinary precision. If the quantum field theory calculation were actually correct, and the vacuum energy density really reached 10 to the 113th power joules per cubic meter, the gravitational consequences would be so catastrophic that the universe as we know it could never have existed. Einstein's general relativity shows that energy and matter curve spacetime with the degree of curvature proportional to the energy density, so the enormous vacuum energy predicted by quantum field theory would create spacetime curvature so extreme that the entire universe would collapse to a singularity in a tiny fraction of a second. Even if the universe somehow managed to begin expanding from a Big Bang, the immense gravitational attraction of the vacuum energy would halt and reverse that expansion almost immediately, causing a big crunch long before the first atoms could form. The predicted vacuum energy would also prevent the formation of any stable structures because its gravitational field would be strong enough to tear apart atomic nuclei, atoms, molecules, and even elementary particles themselves through tidal forces that would make the interior of black holes seem gentle by comparison. Space and time would become so severely distorted that the familiar 3 dimensions of space would curl up into microscopic loops smaller than atomic nuclei, leaving only higher dimensional structures that bear no resemblance to the large-scale cosmos revealed by astronomical observations. The cosmological constant problem gains additional urgency from the fact that both the problematic quantum field theory calculation and the precise astronomical observations that contradict it are based on extremely well-tested physics. Quantum field theory, particularly quantum electrodynamics, has been verified through laboratory experiments to extraordinary precision, with some predictions matching observations to better than 1 part in a trillion, making it the most accurately tested theory in the history of science. Similarly, the astronomical measurements that determine the actual cosmological constant come from multiple independent observational techniques including supernova distance measurements, cosmic microwave background analysis, and large-scale structure surveys, all of which consistently point toward the same small value for dark energy density. The reliability of both the theoretical framework and the observational evidence makes the vacuum catastrophe especially troubling because it cannot be easily dismissed as arising from experimental error or theoretical oversimplification. Numerous attempts to resolve this discrepancy have been proposed over the decades since the problem was first recognized, but none has achieved widespread acceptance among physicists. Supersymmetry theories suggest that the zero-point energies of bosonic and fermionic fields might cancel each other exactly, but supersymmetry must be broken at low energies to match experimental observations, and any realistic breaking mechanism reintroduces vacuum energy contributions that are still many orders of magnitude larger than observations allow. String theory offers the possibility that extra spatial dimensions might affect vacuum energy calculations, but concrete string theory models generally predict cosmological constants that are either zero or enormously larger than observed, failing to explain the small but non-zero value detected by astronomers. Some theorists have proposed that the vacuum energy is exactly zero due to some unknown fundamental symmetry, with dark energy arising from entirely different physics such as quintessence fields or modifications to general relativity, but these proposals generally lack compelling theoretical motivation and often introduce new fine-tuning problems of their own. The anthropic principle has been invoked to argue that we observe a small cosmological constant because universes with larger vacuum energies would be uninhabitable, but this approach requires accepting a multiverse of different vacuum states and abandons the traditional goal of predicting unique values for fundamental constants from first principles. Despite decades of intensive research by theorists worldwide, the cosmological constant problem remains as mysterious and embarrassing today as when it was first recognized, standing as a constant reminder that our understanding of the relationship between quantum mechanics and gravity remains fundamentally incomplete and may require revolutionary new insights to resolve. The cosmological constant problem has inspired decades of theoretical proposals attempting to explain why the vacuum energy density is so much smaller than quantum field theory predicts, yet none has achieved definitive success in resolving the most embarrassing discrepancy in physics. Supersymmetry emerged as one of the most promising early solutions, proposing that every boson has a corresponding fermionic superpartner and vice versa, creating a fundamental symmetry between particles with integer and half-integer spin. In supersymmetric theories, the zero-point energies of bosonic fields contribute positive vacuum energy while fermionic fields contribute negative vacuum energy, and if supersymmetry were exact, these contributions would cancel perfectly to yield zero total vacuum energy. However, experimental searches have found no evidence for supersymmetric particles at accessible energy scales, indicating that supersymmetry must be broken in the real world, and any realistic supersymmetry breaking mechanism reintroduces vacuum energy contributions that remain many orders of magnitude larger than astronomical observations allow. Even the most carefully designed supersymmetric models struggle to suppress the vacuum energy below 10 to the power of 60 joules per cubic meter, still 69 orders of magnitude larger than the observed cosmological constant. String theory, which attempts to unify all fundamental forces, including gravity, within a single theoretical framework, initially offered hope for resolving the vacuum energy crisis through its prediction of extra spatial dimensions and novel mechanisms for determining vacuum structure. However, string theory's treatment of vacuum energy has revealed additional complications rather than clear solutions. Most string theory constructions naturally produce either exactly zero cosmological constant or values that are much larger than observations, with relatively few models yielding the small positive value that dark energy observations require. Furthermore, string theorists have argued that universes with positive cosmological constants, called de Sitter spaces, may be fundamentally incompatible with string theory's mathematical structure because they possess event horizons that prevent the construction of a well-defined scattering matrix, potentially ruling out string theory as a description of our accelerating universe. Some string theorists have proposed mechanisms involving flux compactification and moduli stabilization that might generate small positive cosmological constants, but these constructions typically require enormous fine-tuning of parameters and have not led to definitive predictions that can be tested experimentally. The anthropic principle represents a more radical approach to the cosmological constant problem, arguing that we observe a small vacuum energy density not because fundamental physics demands it, but because universes with substantially different values would be uninhabitable. According to anthropic reasoning, If the cosmological constant were much larger, cosmic acceleration would have prevented the formation of galaxies and stars, necessary for the development of complex chemistry and life. While if it were much smaller or negative, the universe might have collapsed before biological evolution could occur. This anthropic approach requires accepting the existence of a vast multiverse containing regions with different values of the cosmological constant, allowing the anthropic principle to select the narrow range of values compatible with the existence of observers. Multiverse theories provide the theoretical framework needed for anthropic solutions, proposing mechanisms such as eternal inflation or string theory, landscape scenarios that generate enormous numbers of causally disconnected regions with different physical constants and vacuum energies. While anthropic arguments can potentially explain the observed value of the cosmological constant, many physicists find this approach unsatisfying because it abandons the traditional goal of deriving unique predictions from fundamental theory and instead relies on probabilistic arguments about which universes are more likely to contain observers. Recent theoretical developments have introduced new approaches to the cosmological constant problem that attempt to modify the relationship between vacuum energy and space-time curvature rather than eliminating the vacuum energy itself. Lucas Lombreiser at the University of Geneva proposed in 2021 that the cosmological constant might be dynamically constrained by the finite size of the observable universe rather than determined by local quantum field theory calculations. His approach introduces additional field equations derived from varying the gravitational action with respect to quantities that describe the global structure of spacetime, potentially explaining why vacuum energy does not gravitate in the same way as ordinary matter and energy. Lombreiser's mechanism suggests that the cosmological constant adjusts itself to a value determined by the total volume and matter content of the observable universe, providing a potential resolution that connects the cosmological constant problem to the fundamental structure of spacetime itself. While promising, these recent proposals remain highly speculative and require further development to determine whether they can provide complete and testable solutions to the vacuum energy crisis that has plagued theoretical physics for more than half a century. The prediction that quantum vacuum fluctuations contain enormous energy densities has inspired decades of speculation about tapping this supposedly limitless reservoir for practical power generation, creating a modern version of the ancient dream of perpetual motion that has captured imaginations from science fiction writers to fringe inventors to serious NASA researchers. The seductive appeal of zero-point energy extraction begins with the naive quantum field theory calculation, suggesting that every cubic centimetre of empty space contains more energy than burning a tank of gasoline, leading to visions of inexhaustible power supplies that could revolutionise human civilization by providing clean, abundant energy without fuel, waste, or environmental impact. Popular science fiction franchises have embraced this concept enthusiastically, with Star Trek's quantum torpedoes supposedly deriving extra destructive power from vacuum energy extraction, while Stargate's zero-point modules represent advanced alien technology that powers entire civilizations by harvesting energy from microscopic parallel universes connected to our own through quantum mechanical tunneling effects. These fictional depictions, while scientifically implausible, have contributed to widespread public fascination with zero-point energy as a potential solution to humanity's energy challenges, inspiring countless internet forums, patent applications, and entrepreneurial ventures claiming to have developed practical devices for extracting usable power from the quantum vacuum. The persistence of free energy claims based on zero-point energy extraction reflects both the genuine mystery surrounding vacuum energy calculations and the fundamental misunderstanding of how energy conservation operates in quantum mechanical systems. Promoters of zero-point energy devices typically point to the Casimir effect as proof that vacuum energy can produce measurable forces, arguing that if virtual particles can push metal plates together, they should also be capable of turning generators, powering motors, and providing unlimited electricity for human consumption. These claims usually ignore the crucial fact that the Casimir effect represents a redistribution of existing vacuum energy rather than net energy extraction, with the attractive force between conducting plates arising from differences in vacuum energy density rather than creation of new energy from nothing. Professional scientists and patent offices have encountered thousands of proposed zero-point energy extraction devices over the past several decades, ranging from simple electromagnetic circuits claimed to amplify vacuum fluctuations to elaborate mechanical systems supposedly capable of converting virtual particles, motion into useful work. None of these devices has ever demonstrated energy output exceeding energy input under controlled testing conditions, and most fail to produce any anomalous effects whatsoever when properly isolated from external power sources and electromagnetic interference. Nevertheless, the theoretical possibility that advanced understanding of quantum vacuum physics might eventually enable some form of energy extraction has motivated studious research at several prestigious institutions, most notably NASA's EagleWorks laboratory at the Johnson Space Center in Houston. The NASA Advanced Propulsion Physics Laboratory, commonly known as EagleWorks, has investigated a wide range of exotic propulsion concepts, including proposals for vacuum energy utilization, warp drive physics, and electromagnetic drives that seemingly violate conservation of momentum. Under the direction of Harold White, EagleWorks researchers have tested devices such as the controversial M-drive, which claims to generate thrust without expelling reaction mass by creating asymmetric electromagnetic fields inside a closed cavity, potentially deriving momentum from quantum vacuum fluctuations through mechanisms that remain poorly understood. While most physicists remain deeply skeptical of these claims, NASA's willingness to investigate such exotic concepts reflects both the enormous potential payoff of breakthrough propulsion technology for space exploration and the recognition that our understanding of vacuum physics remains incomplete enough to warrant careful experimental investigation. The theoretical foundation for zero-point energy extraction typically relies on proposals for manipulating vacuum energy density through exotic electromagnetic field configurations, metamaterial structures with unusual optical properties, or quantum mechanical systems that might be capable of converting virtual particle fluctuations into real particle production. Some researchers have proposed using rapidly oscillating electromagnetic fields to create dynamic Casimir effects that convert virtual photons into detectable radiation, while others have suggested that carefully designed cavity geometries might enable extraction of energy from vacuum fluctuations through resonance effects or nonlinear interactions between electromagnetic fields and quantum vacuum states. However, all such proposals face the fundamental challenge that the quantum vacuum represents the lowest possible energy state of all quantum fields, meaning that any extraction of energy from vacuum fluctuations would require reducing the vacuum to a state with less than zero-point energy, which the uncertainty principle explicitly forbids. This basic thermodynamic constraint suggests that practical zero-point energy extraction may be fundamentally impossible rather than merely technically challenging, relegating vacuum energy devices to the same category as classical, perpetual motion machines that violate well-established conservation laws. Despite the enormous energy densities predicted by quantum field theory calculations, the fundamental laws of thermodynamics impose strict constraints on any practical extraction of zero-point energy that effectively prohibit the kind of unlimited power generation that popular speculation often envisions. The first law of thermodynamics, which mandates that energy cannot be created or destroyed, but only converted from one form to another, applies with full force to quantum mechanical systems, including those involving vacuum energy fluctuations. This conservation principle means that any device claiming to extract energy from the quantum vacuum must either draw that energy from some external source, convert one form of energy into another, or operate as a temporary energy storage and release system rather than a true energy generator. The quantum vacuum represents the lowest possible energy state that quantum fields can achieve, analogous to a ball sitting at the bottom of a valley from which it cannot roll any lower, without violating basic principles of physics. Attempting to extract energy from this ground state would require forcing the vacuum into a configuration with less than zero-point energy, which the uncertainty principle explicitly forbids because it would demand perfect knowledge of field values and their rates of change simultaneously. Even the most sophisticated proposals for vacuum energy extraction ultimately face this fundamental constraint, requiring energy input to create the conditions under which vacuum energy might be redistributed or converted into useful forms, ensuring that the total energy output cannot exceed the energy invested in the extraction process. The principle of detailed balance, which governs the behavior of quantum systems in thermal equilibrium, provides another powerful constraint on zero-point energy utilization, by requiring that any process capable of extracting energy from vacuum fluctuations must be balanced by an equally probable reverse process that returns energy to the vacuum state. In thermal equilibrium, the rates of all forward and reverse quantum processes must balance exactly, preventing any net flow of energy from the vacuum into macroscopic systems that could be harnessed for practical applications. This balance ensures that while individual quantum events may temporarily redistribute vacuum energy among different field modes, the average energy flow over longer timescales remains exactly zero, eliminating any possibility for sustained power generation from vacuum fluctuations alone. Laboratory investigations of proposed zero-point energy extraction devices have consistently confirmed these thermodynamic constraints, with careful measurements showing that apparent energy anomalies invariably result from experimental errors, unrecognized energy inputs, or misinterpretation of measurement data, rather than genuine violations of energy conservation. Independent testing. Facilities including those operated by the US Patent Office, various national laboratories, and academic research institutions have evaluated hundreds of claimed zero-point energy devices over the past several decades without finding a single example that produces net energy output under controlled conditions that eliminate external power sources and electromagnetic interference. The most sophisticated tests involve placing alleged energy extraction devices inside Faraday cages that block external electromagnetic fields, monitoring them with sensitive calorimeters that can detect tiny heat flows, and comparing their energy output to detailed accounting of all possible energy inputs, including electrical power, mechanical work, chemical reactions, and ambient thermal fluctuations. These rigorous evaluations consistently reveal that devices claiming to harvest vacuum energy either produce no measurable output whatsoever or demonstrate energy outputs that precisely match identifiable energy inputs when all sources are properly accounted for. Even the genuine quantum mechanical effects that involve vacuum energy, such as the Casimir effect and spontaneous emission, operate within strict thermodynamic constraints that prevent energy extraction beyond what is consistent with energy conservation. The attractive force between Casimir plates, for example, can perform mechanical work by bringing the plates together, but the energy for this work comes from the external agent that initially separated the plates against the Casimir attraction rather than from the vacuum itself. Similarly, spontaneous emission by excited atoms involves energy that was previously stored in the atomic excitation rather than newly created from vacuum fluctuations, with the vacuum fluctuations serving as a catalyst for energy release rather than an energy source. Quantum energy teleportation experiments, which represent some of the most sophisticated manipulations of vacuum energy achieved to date, demonstrate energy transfer processes that rigorously respect conservation laws by ensuring that energy extracted at one location is precisely balanced by energy injection at another location, resulting in zero net energy production. The thermodynamic analysis of these experiments reveals that quantum field fluctuations can facilitate energy redistribution and enable novel forms of energy storage and transfer, but they cannot serve as sources of unlimited energy that violate fundamental conservation principles. Modern theoretical frameworks including quantum field theory, statistical mechanics, and general relativity all converge on the conclusion that the quantum vacuum, despite its complex and energetic fluctuation patterns, represents a stable equilibrium state from which net energy extraction is thermodynamically impossible, relegating zero-point energy devices to the same category of impossible machines as classical perpetual motion devices that attempt to violate energy. Conservation through mechanical, electrical, or chemical means. While zero-point energy cannot provide unlimited power generation, vacuum fluctuations and quantum field effects have found genuine practical applications in cutting-edge technologies ranging from micro-electromechanical systems to quantum computing and precision instrumentation. The Casimir effect has become particularly important in the design and operation of MEMS devices, where components separated by nanometer-scale gaps experience significant attractive forces that can interfere with normal operation or be harnessed for specific functionalities. Engineers designing microactuators, nanosensors, and quantum devices must carefully account for Casimir forces that become dominant at separations below 1 micrometer, often requiring specialized surface treatments, geometric modifications, or active compensation systems to prevent unwanted stiction that could permanently damage delicate mechanical components. Some advanced MEMS designs deliberately exploit Casimir attraction to create ultra-sensitive force sensors, precision positioning systems, and novel actuators that operate without requiring external power sources beyond the energy needed to initially separate their components. Recent developments in quantum random number generation have demonstrated practical applications of vacuum fluctuations for cryptography and secure communications, with researchers at Ghent University in Belgium developing systems that achieve random number generation rates up to 200 times faster than conventional electronic devices by monitoring quantum fluctuations in electromagnetic fields. These quantum random number generators operate by measuring the inherently unpredictable timing and amplitude variations in vacuum fluctuations, converting the fundamental randomness of quantum mechanics into bit streams that are provably free from patterns or correlations that could compromise cryptographic security. The technology has attracted significant commercial interest because traditional random number generators based on electronic noise or algorithmic processes can potentially be predicted or manipulated by sophisticated attackers, while quantum vacuum fluctuations provide randomness that is guaranteed by the fundamental laws of physics rather than depending on the complexity of classical deterministic processes. In 2024, researchers at MIT achieved a breakthrough in controlling vacuum fluctuations using intense laser fields, demonstrating the ability to manipulate quantum field fluctuations in free space and harness them for probabilistic computing applications. Their technique involves using carefully shaped laser pulses to modify the local properties of the electromagnetic vacuum, creating controlled variations in quantum fluctuation patterns that can be detected and processed as random bit sequences for quantum computing algorithms. This laser-controlled vacuum manipulation represents the first practical method for engineering quantum fluctuations outside of specialized cavity environments, opening possibilities for portable quantum technologies that do not require bulky superconducting systems or ultra-high vacuum chambers. The MIT experiments also demonstrated that vacuum fluctuations can be used to generate quantum entanglement between distant locations, potentially enabling new forms of quantum communication and distributed quantum computing that rely on the universal properties of empty space rather than specially prepared quantum materials. Quantum energy teleportation protocols, first proposed theoretically in 2008 and successfully demonstrated in laboratory experiments starting in 2019, represent perhaps the most sophisticated practical application of vacuum energy manipulation achieved to date. These experiments show that energy extracted from vacuum fluctuations at one location can be instantaneously transferred to distant locations through quantum entanglement effects, enabling new forms of energy distribution and storage that operate faster than light speed, while rigorously respecting energy conservation laws. Research teams in Germany and Japan have successfully implemented quantum energy teleportation using trapped atomic systems and superconducting quantum circuits, demonstrating energy transfer efficiencies that approach theoretical limits while maintaining the quantum coherence needed for practical applications in quantum computing and quantum sensing. The technology has potential applications in quantum battery systems, where energy could be stored in quantum field fluctuations and retrieved on demand without the losses associated with conventional energy storage methods. Nanotechnology applications of vacuum effects include advanced stiction control systems that use engineered surface textures and electromagnetic fields to modify Casimir forces between closely spaced components in molecular scale machines and nano-electromechanical systems. Researchers have developed metamaterial surfaces with specially designed electromagnetic properties that can create repulsive Casimir forces under certain conditions, enabling contactless suspension and manipulation of nanoparticles and molecular assemblies without mechanical contact that could cause damage or contamination. These anti-stiction technologies are becoming essential for the development of molecular machines, DNA manipulation devices, and precision manufacturing systems that operate at scales where quantum effects dominate over classical mechanical forces. Current research in vacuum engineering focuses on developing programmable quantum field environments where the properties of empty space can be dynamically controlled through external electromagnetic fields, engineered boundary conditions, and novel material interactions, potentially enabling a new generation of quantum technologies that harness the fundamental properties of vacuum fluctuations for practical applications in computing, sensing, communication, and precision measurement. The discovery that conducting and dielectric boundaries can alter the quantum vacuum state has opened the theoretical possibility of vacuum engineering, where the energy density and force characteristics of empty space are deliberately modified through carefully designed electromagnetic environments and boundary conditions. This concept emerged from the recognition that the Casimir effect represents only the simplest example of how material boundaries influence vacuum energy, with more complex geometries and material properties offering opportunities for sophisticated manipulation of quantum field fluctuations. When conducting plates are introduced into the vacuum, they exclude certain electromagnetic modes from the region between them, while leaving other modes unchanged, effectively creating spatial variations in vacuum energy density that manifest as measurable forces. More elaborate conductor arrangements, including spherical cavities, cylindrical geometries, and complex three-dimensional structures, each create their own unique patterns of vacuum energy modification, with some configurations producing attractive forces, others generating repulsion, and still others creating torques or lateral forces that depend on the relative orientations and positions of the conducting boundaries. Dielectric materials offer additional possibilities for vacuum manipulation because their frequency-dependent electromagnetic properties can selectively affect different wavelengths of quantum fluctuations, creating spectral filtering effects that modify vacuum energy density in ways that depend on the detailed optical properties of the materials involved. Recent theoretical work has shown that metamaterials with engineered electromagnetic responses can produce vacuum energy effects that have no natural analogue, including negative index materials that reverse the usual relationship between electromagnetic fields and their sources, and materials with extreme anisotropy that create vacuum energy densities that vary dramatically with direction. The concept of Casimir cavity energy extraction was first seriously analysed by Robert Forward at Hughes Research Laboratories in 1984, who proposed that vacuum energy might be temporarily stored and released using dynamic cavity systems with time-varying boundary conditions. Forward's theoretical analysis showed that rapidly changing the size or shape of a Casimir cavity could potentially convert some of the vacuum energy into detectable electromagnetic radiation through a process analogous to the dynamical Casimir effect. But his calculations also revealed that the energy extraction efficiency would be extremely low and would require energy input to drive the cavity changes. His proposed vacuum battery concept involved creating multiple nested Casimir cavities with different resonant frequencies, allowing vacuum energy to be transferred between cavities through controlled coupling effects and potentially concentrated for brief periods in ways that might enable practical energy storage and release. While Forward's calculations showed that such vacuum batteries could not violate thermodynamic conservation laws, they suggested that vacuum energy manipulation might enable novel forms of energy storage with unique properties, including potentially unlimited storage lifetimes and storage densities that could exceed those of conventional battery technologies. Modern theoretical investigations of vacuum engineering have extended these early concepts to include proposals for programmable vacuum environments where the local properties of empty space could be dynamically controlled through external electromagnetic fields, engineered metamaterial structures, and quantum field manipulation techniques. These advanced vacuum engineering concepts include proposals for vacuum waveguides that could transmit energy and information through controlled manipulation of quantum field modes, vacuum amplifiers that might enhance weak signals by coupling them to vacuum fluctuations in cavity resonators, and vacuum transistors that could switch and modulate electromagnetic fields by altering the vacuum state in semiconductor structures with voltage-controlled optical properties. Theoretical studies have also explored the possibility of creating vacuum energy gradients that could exert forces on neutral matter through polarization effects, potentially enabling new forms of contactless manipulation and propulsion that operate through quantum field interactions rather than conventional electromagnetic or mechanical forces. Some researchers have proposed using superconducting circuits with time-varying parameters to create artificial gauge fields that could trap and manipulate vacuum energy fluctuations, while others have suggested that topological quantum states in condensed matter systems might provide platforms for realizing exotic vacuum energy effects that cannot occur in free space. The mathematical framework for vacuum engineering draws on sophisticated techniques from quantum field theory, condensed matter physics, and electromagnetic theory to predict how complex boundary conditions and material properties affect the quantum vacuum state. These calculations often reveal that seemingly small changes in boundary geometry or material composition can produce dramatic alterations in vacuum energy density and force characteristics, suggesting that practical vacuum engineering might be achievable with relatively modest technological advances in metamaterial fabrication and electromagnetic control systems. However, all theoretical proposals for vacuum engineering must confront the fundamental constraint that the quantum vacuum represents the lowest possible energy state of quantum fields, limiting vacuum manipulation to energy redistribution and conversion processes rather than net energy extraction from the vacuum state itself. Current research in vacuum engineering has advanced far beyond theoretical speculation to encompass sophisticated experimental programs and practical device development that exploit quantum vacuum properties for next-generation technologies. Many-body quantum vacuum engines represent one of the most promising frontiers, where researchers design complex quantum systems with multiple interacting components that can collectively harness vacuum fluctuations to perform useful work while operating within thermodynamic constraints. These engines typically involve arrays of quantum dots, superconducting qubits, or trapped atomic systems that are coupled to engineered electromagnetic environments where vacuum fluctuations can drive energy transfer between different components of the system. Teams at institutions including MIT, ETH Zurich, and the University of Vienna have demonstrated proof-of-concept quantum engines that extract work from temperature differences between different vacuum modes, showing that carefully designed many-body systems can convert thermal vacuum fluctuations into mechanical motion, electrical current, or stored quantum energy. The key insight driving this research is that, while the total vacuum energy cannot be reduced, its distribution among different quantum modes can be manipulated to create useful energy flows that respect conservation laws while enabling practical applications. Superconducting circuit applications of vacuum engineering have emerged as particularly fertile ground for technological development because these systems offer precise control over electromagnetic boundary conditions at microwave frequencies where vacuum effects become experimentally accessible. Research groups worldwide have developed superconducting quantum interference devices, flux qubits, and transmission line resonators that can detect and manipulate quantum vacuum fluctuations with extraordinary sensitivity, achieving coupling strengths between artificial atoms and vacuum modes that exceed what is possible with natural atomic systems. These superconducting vacuum manipulation systems have enabled the first experimental demonstrations of quantum energy teleportation, dynamic Casimir effect generation, and vacuum-mediated entanglement between distant quantum processors. Companies including IBM, Google, and Rigetti Computing are investigating how vacuum engineering techniques might enhance quantum computer performance by reducing decoherence, improving qubit coupling, and enabling new forms of quantum error correction that exploit the universal properties of electromagnetic vacuum fluctuations. Quantum vacuum fluctuation rectification represents an emerging field focused on developing devices that can convert the random fluctuations of quantum fields into directed energy flows, analogous to how semiconductor diodes convert alternating current into direct current. Researchers have proposed and begun testing quantum rectifiers based on asymmetric electromagnetic structures, nonlinear optical materials, and time-varying boundary conditions that preferentially amplify vacuum fluctuations in one direction while suppressing them in others. Early experiments using metamaterials with engineered nonlinear responses have demonstrated small but measurable rectification effects that convert isotropic vacuum fluctuations into directed electromagnetic fields, though the efficiency of these processes remains far below what would be needed for practical energy applications. The theoretical framework for vacuum rectification suggests that more sophisticated designs involving quantum coherence effects and many-body interactions might achieve substantially higher efficiencies while maintaining compatibility with fundamental thermodynamic constraints. Space-time engineering proposals represent the most ambitious frontier of vacuum research, where scientists explore the possibility that sufficiently advanced manipulation of quantum vacuum properties might enable control over the geometry and topology of space-time itself. These investigations build on theoretical insights from general relativity and quantum field theory, suggesting that vacuum energy fluctuations contribute to space-time curvature, and that modified vacuum states might produce exotic gravitational effects including negative energy densities, closed time-like curves, and traversable wormhole geometries. While most spacetime engineering concepts remain highly speculative and far beyond current technological capabilities, Some researchers have identified potentially achievable scenarios involving intense electromagnetic fields, exotic matter, configurations, or engineered quantum field states that might produce measurable modifications to local space-time geometry. The Breakthrough Starshot project has specifically investigated whether vacuum engineering techniques might enable new forms of interstellar propulsion that do not require carrying reaction mass, focusing on concepts including photon sailing enhanced by vacuum interactions, electromagnetic drives that couple to quantum vacuum fluctuations, and exotic propulsion mechanisms that might exploit negative energy effects predicted by certain quantum field theories. Project scientists have analysed proposals for ultra-lightweight spacecraft powered by controlled interactions with the quantum vacuum, though current analysis suggests that even the most optimistic vacuum engineering scenarios would provide thrust levels far below what conventional propulsion systems can achieve. Nevertheless, the Breakthrough Starshot investigations have contributed valuable insights into the fundamental limits of vacuum manipulation and have identified specific research directions that might eventually lead to practical vacuum-based propulsion technologies, even if current proposals cannot provide the dramatic performance enhancements that interstellar travel applications would require. The future of vacuum engineering holds remarkable possibilities for technologies that could revolutionize fields from nanotechnology to space exploration, though realistic expectations must acknowledge fundamental physical constraints that will likely prevent the unlimited energy extraction scenarios popularized in science fiction. Repulsive Casimir forces represent one of the most immediately achievable advances, where researchers have already demonstrated that certain combinations of materials immersed in appropriate fluids can produce quantum vacuum effects that push objects apart rather than pull them together. Jeremy Munday and Federico Capasso at Harvard University successfully measured repulsive Casimir forces between gold surfaces separated by bromobenzene, confirming theoretical predictions that the electromagnetic properties of intervening media can reverse the usual attractive vacuum effect. This discovery opens possibilities for contactless levitation systems, frictionless bearings, and microscale machines that operate without mechanical contact by balancing repulsive Casimir forces against gravity or other applied forces. Future applications might include self-assembling nanostructures that organize themselves through programmed patterns of attractive and repulsive vacuum interactions, ultra-precise positioning systems for atomic-scale manufacturing, and biological manipulation devices that can move cells and molecules without physical contact that might cause damage or contamination. Metamaterial vacuum engineering represents perhaps the most promising avenue for advanced vacuum manipulation technologies, building on rapid advances in artificial electromagnetic materials with properties that do not occur naturally. Researchers are developing metamaterials with negative refractive indices, extreme anisotrope, and time-varying electromagnetic responses that can create unprecedented control over quantum field fluctuations in their vicinity. These engineered materials might enable vacuum waveguides that channel electromagnetic energy through controlled modification of local vacuum properties, vacuum amplifiers that enhance weak signals by coupling them to quantum fluctuations, and programmable vacuum environments where the electromagnetic properties of empty space can be dynamically reconfigured through external control signals. Future metamaterial designs incorporating active elements, quantum coherence effects, and topological properties could potentially create vacuum manipulation capabilities that approach the theoretical limits imposed by fundamental physics, enabling applications including ultra-sensitive detectors that exploit vacuum fluctuation enhancement, quantum computing systems that use vacuum engineering for error, correction, and qubit coupling, and precision measurement instruments that achieve sensitivity beyond the standard quantum limit through vacuum field manipulation. Quantum vacuum thrusters represent one of the most speculative but potentially revolutionary applications of vacuum engineering, where spacecraft might generate propulsion by creating asymmetric interactions with quantum field fluctuations. While current proposals for vacuum-based propulsion remain far below the performance levels needed for practical space applications, ongoing research into dynamic Casimir effects, quantum field rectification, and electromagnetic momentum transfer suggests that more sophisticated vacuum manipulation techniques might eventually achieve measurable thrust generation. NASA's EagleWorks laboratory and other research institutions continue investigating whether carefully designed electromagnetic field configurations might couple spacecraft momentum to quantum vacuum fluctuations, though Theoretical analysis indicates that any such effects would likely produce extremely small forces requiring enormous technological advances to become practically useful for space exploration. Zero-point energy storage systems could potentially exploit vacuum engineering to create novel energy storage mechanisms with unique properties including unlimited storage lifetimes and storage densities that exceed conventional battery technologies, though such systems would still be constrained by thermodynamic conservation laws that prevent net energy extraction from the vacuum state. Theoretical proposals include vacuum battery concepts where energy is temporarily stored in modified vacuum field configurations and retrieved through controlled manipulation of electromagnetic boundary conditions, quantum capacitors that store energy in coherent vacuum fluctuation patterns, and vacuum energy concentrators that redistribute quantum field energy to enable high-density energy storage for brief periods. However, realistic expectations for future vacuum engineering must acknowledge several fundamental limitations that will likely prevent the most dramatic applications envisioned by popular speculation. The quantum vacuum represents the lowest possible energy state of all quantum fields, meaning that vacuum energy can be redistributed and converted between different forms but cannot be extracted to provide unlimited power generation. Thermodynamic constraints ensure that any practical vacuum engineering device must consume more energy than it produces, limiting applications to energy conversion, storage and manipulation rather than energy creation. Additionally, the extremely small energy scales associated with most quantum vacuum effects mean that even highly efficient vacuum engineering systems would likely produce only modest performance improvements over conventional technologies, except in specialized applications where quantum effects become dominant, such as nanoscale systems, ultra-sensitive measurements, and quantum information processing, where vacuum engineering might provide crucial advantages unavailable through classical approaches. The reason we don't directly perceive the vast quantities of vacuum energy that quantum field theory predicts lies in the fundamental nature of how energy is measured and how gravity responds to different forms of energy density, creating one of the most subtle and profound puzzles in modern physics. Our everyday experience of energy involves differences and changes rather than absolute values, much like how we perceive temperature through heat flow rather than absolute thermal energy content, which means that a uniform background of vacuum energy remains completely invisible to all conventional measurement techniques. The human body evolved to detect energy through interactions with matter and radiation that deviate from equilibrium states, so the zero-point energy that permeates every cubic centimeter of space cannot be sensed because it represents the baseline against which all other energies are measured. Every energy measurement we perform, from chemical reactions to nuclear processes to electromagnetic phenomena, involves differences between initial and final energy states rather than absolute energy values, and since vacuum energy contributes equally to all quantum states, it cancels out of every observable quantity that laboratory physics can directly access. Even our most sophisticated instruments, including calorimeters, particle detectors, and gravitational wave observatories, can only measure energy changes and energy flows rather than the static energy content of empty space, making vacuum energy fundamentally undetectable through local experiments performed within regions where the vacuum properties remain constant. The gravitational effects of vacuum energy present an even deeper mystery, because general relativity clearly states that all forms of energy density should curve spacetime and contribute to cosmic evolution, yet the enormous vacuum energy predicted by quantum field theory would create gravitational effects so extreme that no stable structures could exist in the universe. If the quantum field theory calculation were correct and vacuum energy density really reached 10 to the 113th power joules per cubic meter, the resulting space-time curvature would be so intense that the entire observable universe would collapse to a singularity in a time much shorter than the age of a proton, preventing the formation of atoms, stars, galaxies, or any complex structures that require billions of years of cosmic evolution to develop. The fact that we observe a universe with gentle space-time curvature and stable large-scale structure indicates that either the quantum field theory prediction is fundamentally incorrect, or that some unknown physics prevents vacuum energy from gravitating in the same way as ordinary matter and energy. The cosmological constant that drives cosmic acceleration corresponds to a vacuum energy density of approximately 10 to the negative 9th power joules per cubic meter, which is so much smaller than the quantum field theory prediction that it suggests either an extraordinary, fine-tuning conspiracy where enormous positive and negative contributions cancel to 123 decimal places, or a complete breakdown in our understanding of how quantum mechanics and gravity interact at cosmic scales. Reference frame dependencies add another layer of complexity to the vacuum energy measurement problem, because different observers in relative motion or different gravitational fields will generally disagree about the energy content of quantum field fluctuations, creating apparent paradoxes where vacuum energy seems to depend on the observer, rather than representing an objective property of space-time itself. Special relativity shows that electromagnetic field energy transforms between different inertial frames in ways that depend on relative velocities and field orientations, suggesting that quantum vacuum energy might also be observer-dependent in ways that could resolve some of the apparent contradictions between quantum field theory and gravitational observations. However, attempts to use relativity to eliminate vacuum energy through appropriate coordinate transformations have generally failed because the quantum vacuum state is defined to be invariant under Lorentz transformations, meaning that all inertial observers should agree about vacuum energy density, even if they disagree about other electromagnetic field properties. The challenge of reconciling observational and theoretical approaches to vacuum energy reflects deeper issues with how quantum field theory handles infinite quantities and how those infinities relate to measurable physical effects. Theoretical calculations of vacuum energy typically involve summing over infinitely many quantum field modes, requiring mathematical regularization and renormalization techniques that introduce arbitrary cutoff parameters whose physical meaning remains unclear. Different regularization schemes can yield vacuum energy predictions that differ by enormous factors, suggesting that the quantum field theory approach to vacuum energy calculations may be fundamentally flawed rather than simply technically difficult. Observational astronomy provides increasingly precise measurements of the actual vacuum energy density through studies of cosmic acceleration, cosmic microwave background fluctuations, and large-scale structure formation, but these observations measure the effective gravitational properties of vacuum energy rather than its microscopic quantum mechanical origins. The disconnect between theoretical predictions and observational constraints suggests that resolving the vacuum energy puzzle may require revolutionary advances in our understanding of quantum gravity, the nature of spacetime at microscopic scales, or the fundamental relationship between quantum mechanics and general relativity that goes far beyond simply improving computational techniques or experimental precision. The deepest implications of vacuum energy research suggest that what we call empty space may actually represent the most fundamental level of reality, with all matter and energy existing as mere ripples on an ocean of quantum activity that never stops fluctuating, even in the apparent absence of everything else. Modern quantum field theory describes particles not as tiny billiard balls moving through space, but as localized excitations of underlying quantum fields that extend throughout the universe, meaning that an electron is really a wave-like disturbance in the electron field. A photon represents an excitation of the electromagnetic field, and even the Higgs boson emerges as a vibration in the Higgs field that permeates all of space and gives mass to other particles through its interactions. This perspective fundamentally inverts our intuitive understanding of matter and emptiness, suggesting that the vacuum itself is the primary reality, while particles represent temporary departures from the ground state of universal quantum fields. From this viewpoint, empty space becomes the most active and information-rich environment in the universe, crackling with virtual particle creation and annihilation events, zero-point field oscillations, and quantum correlations that extend across cosmic distances through entanglement effects that operate faster than light yet never violate causality. The apparent solidity and permanence of matter emerges as a collective illusion arising from the synchronized behavior of countless quantum field excitations, much like how a seemingly solid wave on the ocean surface is actually composed of water molecules that move in complex patterns without any individual molecule traveling along with the wave. This quantum field picture suggests that consciousness and observation may play more fundamental roles in physical reality than classical physics assumed, since quantum mechanics requires the concept of measurement to determine when wave functions collapse and virtual possibilities become actual outcomes. The measurement problem in quantum mechanics becomes even more mysterious when applied to vacuum fluctuations, because the act of observing quantum fields necessarily disturbs the vacuum state and creates real particles from virtual ones, suggesting that consciousness may literally participate in the creation of physical reality through the process of observation. Some interpretations of quantum mechanics propose that consciousness represents a special type of information processing that can collapse quantum superpositions and convert potential realities into actual ones, which would make conscious observers active participants in the fundamental workings of the universe rather than passive recipients of pre-existing information. The quantum vacuum serves as a hidden machinery that enables all physical processes while remaining essentially invisible to direct detection, operating like the stage on which the drama of existence unfolds without ever appearing as an actor in that drama. Virtual particles mediating forces between real particles, zero-point fluctuations triggering spontaneous emission and decay processes, vacuum polarization modifying the apparent properties of matter, and Casimir effects demonstrating that empty space can exert mechanical forces all reveal that the vacuum participates actively in every physical interaction while maintaining its fundamental invisibility. This hidden machinery extends far beyond the electromagnetic interactions that produce most familiar phenomena, encompassing the quantum chromodynamic vacuum that confines quarks inside protons and neutrons, the weak interaction vacuum that enables radioactive decay and stellar fusion, and potentially gravitational vacuum effects that might determine the large-scale geometry and evolution of spacetime itself. The universe's dependence on vacuum properties suggests that reality operates more like a vast information processing system than a collection of mechanical objects, with quantum fields serving as the hardware that runs the software of physical law through computational processes that occur at every point in space and moment in time. The recognition that empty space contains the blueprint for all possible physical phenomena has profound implications for our understanding of existence, suggesting that information and pattern rather than matter and energy represent the most fundamental constituents of reality. Quantum field fluctuations encode all possible particle interactions, field configurations, and space-time geometries in a kind of cosmic library that contains every story that physics could ever tell, with actual reality representing just one specific narrative selected from infinite possibilities through processes that remain largely mysterious. The study of vacuum energy thus leads inevitably to questions about the nature of existence itself, the role of information and computation in physical processes, and the possibility that consciousness and physical reality are more intimately connected than our everyday experience suggests. As we continue to probe the properties of empty space through increasingly sophisticated experiments and theories, we may discover that the vacuum holds the key not only to understanding dark energy, quantum gravity, and the ultimate fate of the cosmos, but also to comprehending the deepest questions about why anything exists at all and what it means for conscious beings to participate in a universe built from quantum fluctuations in apparently empty space. The future of vacuum energy research promises revolutionary discoveries that will reshape our understanding of fundamental physics through ambitious new observational programs and theoretical investigations that probe ever deeper into the quantum foundations of reality. The Euclid Space Telescope, launched by the European Space Agency in 2003, represents humanity's most sophisticated attempt to measure dark energy properties with unprecedented precision by mapping the three-dimensional distribution of galaxies across cosmic history and determining whether the accelerated expansion of space truly matches the behavior expected from Einstein's cosmological constant or reveals evidence for more exotic explanations, including evolving vacuum energy, extra dimensions, or modifications to general relativity itself. Euclid's observations of billions of galaxies spanning the past 10 billion years of cosmic evolution will measure the expansion rate of the universe to better than 1% accuracy, potentially distinguishing between cosmological constant and quintessence models of dark energy, while testing whether vacuum energy properties have remained constant throughout cosmic history or evolved in ways that could provide clues about the fundamental nature of empty space. The Nancy Grace Roman Space Telescope and the Vera Rubin Observatory will complement Euclid's measurements with even more detailed studies of cosmic acceleration, dark energy clustering, and the relationship between vacuum energy and large-scale structure formation, potentially revealing whether dark energy interacts with matter and radiation in ways that differ from simple cosmological constant behavior. LIGO and future gravitational wave observatories including Virgo, Cagra, and the proposed Einstein telescope are opening entirely new windows into vacuum energy physics by detecting ripples in space-time itself that carry information about quantum vacuum properties in extreme gravitational environments near black holes, neutron stars, and during the moments immediately following cosmic inflation. Gravitational wave observations probe vacuum energy effects that cannot be studied through electromagnetic observations, potentially revealing how quantum field fluctuations behave in strongly curved spacetime and whether vacuum energy contributes to gravitational wave generation, propagation, and detection in ways predicted by quantum field theory. Advanced LIGO experiments are also investigating whether gravitational waves interact with quantum vacuum fluctuations in the detector arms, potentially opening new avenues for studying the relationship between gravity and quantum mechanics through precision measurement of vacuum-mediated effects on gravitational wave signals. Future quantum technology applications of vacuum engineering may revolutionize computing, communication, and sensing through systems that harness quantum field fluctuations for practical applications, including quantum computers that use vacuum entanglement for error-corrected quantum processing, quantum communication networks that distribute cryptographic keys through manipulation of vacuum field correlations, and quantum sensors that achieve measurement precision beyond classical limits by exploiting vacuum fluctuation properties for enhanced sensitivity. Emerging quantum technologies including trapped ion systems, superconducting quantum circuits, and topological quantum computers are already beginning to exploit vacuum engineering techniques for improved performance, and future developments may enable quantum devices that operate primarily through controlled manipulation of empty space rather than conventional matter-based components. The philosophical implications of vacuum energy research extend far beyond technical applications to fundamental questions about the nature of existence, the role of consciousness in physical reality, and the possibility that information processing represents a more fundamental level of description than matter and energy. The recognition that empty space contains vast quantities of energy and information challenges traditional concepts of nothingness and somethingness, while suggesting that reality operates more like a cosmic computation than a mechanical system, with quantum field fluctuations serving as the underlying computational substrate that processes the algorithms of physical law. Studies of quantum vacuum properties may eventually reveal deep connections between physics and mathematics, information theory and consciousness, and local quantum effects and global cosmic evolution that transform our understanding of what it means to exist in a universe built from quantum fluctuations. The wonder that emerges from contemplating the quantum foam beneath everyday reality reflects humanity's growing appreciation that the most fundamental levels of existence involve phenomena so strange and counterintuitive that they challenge our most basic assumptions about space, time, matter, and causality. Every cubic centimetre of apparently empty space contains enough quantum activity to power the observable universe if it could somehow be harnessed. Yet this energy remains forever locked in fluctuations that average to zero while enabling all the physical processes that make complexity, life, and consciousness possible. As we continue probing deeper into the quantum foundations of reality through increasingly sophisticated experiments and theories, we may discover that the vacuum energy mystery holds keys not only to understanding dark energy and quantum gravity, but also to answering the deepest questions about why the universe exists, why its laws take their observed forms, and what role conscious observers play in the cosmic story that began with quantum fluctuations in empty space and culminated in beings capable of contemplating their own existence within the quantum foam that gave them birth. Thank you, dear listener, for drifting through this long journey into the hidden machinery of empty space, where we discovered that nothingness is actually everything, and the quantum foam beneath reality powers the cosmos itself through invisible fluctuations that never rest. If this gentle exploration brought you even a moment of wonder about the virtual particles dancing in the void around you, a quiet tap on subscribe helps keep these midnight stories alive among the stars and reminds me that curiosity still finds its way to thoughtful hearts, like yours. Your presence here, listening to tales of vacuum energy and cosmic mysteries, creates a small community of dreamers who understand that the deepest truths often hide in the spaces between things, in the emptiness that turns out to be fullness beyond imagination. As you close your eyes tonight, remember that you are sleeping under the same sky that emerged from quantum fluctuations billions of years ago, when virtual particles first stirred into the primordial vacuum and gave birth to space, time, and everything we call reality. The zero-point energy that fills the darkness around you connects you to the furthest galaxies through invisible threads of quantum correlation, making you part of a cosmic web woven from the very nothingness that powers existence itself. May your dreams drift peacefully through the quantum foam that surrounds us all, and may you wake tomorrow with fresh wonder, the beautiful mystery of the universe built from the creative power of empty space. Rest well, fellow explorer of the infinite, beneath the gentle hum of quantum fields that sing you softly into sleep.